So let us now have the Euler's circuit. So to solve the Konigsberg bridges problem, we can represent the arrangement of land areas and bridges with a graph. Let each land area be represented by a vertex. So here are our vertices. And connect two vertices with a bridge spanning the corresponding land area. So here are our bridges in each land. So here are the lands which has each vertices. Okay, then the geographic configuration shown in figure 5.3 becomes the graph shown in figure 5.4. Okay, the path in a graph can be thought of as a movement from one vertex to another by transversing edges. We can refer to our movement by vertex letter. So for example, in the graph in figure 5.4, so we have one path would be A, B, A, and then C. If we will be using the figure 5.3, as you can see here, A crossing the bridge B, and then A, and then we have here C. If a path ends at the same vertex at which it started, it is considered closed path or circuit. Now in figure 5.5, the path A, D, F, G, E, B, and A is a circuit because it begins and ends at the same vertex. While the path A, D, F, G, E, then H is not a circuit as the path ends at the different vertex than the one it started. So a circuit that uses every edge, here is the word, every edge, but never uses the same edge twice, it is called the Euler circuit. The path may cross through vertices more than once. So the vertices are these dots, but then our edge are this. Okay, take a look. The path BDF, let's see. Okay, we have B and then D, F, G, H, E, C, B, A, D, G, E, and B in figure 5.5 is a Euler circuit. It begins and ends at the same vertex and uses each degree exactly, or each edge exactly once. Now let us trace the path with our pencil or another color with this one. The path A, B, C, E, H, G, E, B, D, and then A is not a Euler circuit. Why? It is because the path begins and ends at the same vertex, but it does not use edges DF, DG, and FG. Okay, so it says here that every edge, okay, but never uses the same edge twice. It is called the Euler circuit. So this is not a Euler circuit. So Euler essentially proved that the graph in figure 5.4 here could not have the Euler circuit. He accomplished this by examining the number of edges that meet or met at each vertex. So the number of edges that meet at the vertex is called the degree of a vertex. He made the observation that in order to complete the desired path, every time you approach a vertex, you would need to leave that vertex. If you travel through that vertex again, you would again need an approaching edge and a departing edge. So thus, the Euler circuit to exist, the degree of every vertex would have to be an even number. So furthermore, he was able to show that any graph that has every degree to every vertex must have the Euler circuit constantly. Such graphs are called Eulerian. So this Eulerian graph theorem, a connected graph is Eulerian if and only if every vertex of a graph is of even degree. So let us have this example. So which of the following graph has a Euler circuit? In our first graph, the vertices C and D are of odd degree. How can we say so? As you can see here, C, we have 1, 2, and then 3, while our D has also 1, 2, and then 3. So by the Eulerian graph theorem, the graph does not have the Euler circuit. Next, in our second graph, all vertices are of even degree. So by the Eulerian graph theorem, the graph has an Euler circuit. So let us see. In our C, we have here A and then E. In our D, we have here A and then B. In B, we have here E, and then we have D, and then so on and so forth. So this has a Eulerian circuit. Okay? Then the Eulerian graph theorem guarantees that when all vertices of a graph have an even degree, an Euler circuit exists, but it does not tell us how to find one. Because the graph we will examine here are relatively small, we will rely on trial and error to find the Euler circuits. So it is manually be done. There is a systematic method called Fleury algorithm that can be used to find Euler circuits in graph with large number of vertices. Like for example, so let us determine whether the graph shown below is Eulerian. If it is, find the Euler circuit. If it is not, explain how you know. So here is our solution on this graph. So each vertex is of even degree of 2, 4, 6. So by the Eulerian graph theorem, this is a Eulerian. Okay, how can we say so? Like for example, our 2 has 1 and then 2. And then for the 6, I have here 1, 2, 3, 4, 5, and then 6. What about the 4? I have here 4, 1, 2, 3, and then 4. So there are many possible Euler circuits in this graph. So we do not have a formal method of locating one, but by trial and error, one Euler circuit is we have there A, F, B, and then we have E, F, G, then E, D, G, B, D, C, and then B. So we have there the Euler circuit wherein we pass through one edge and we did not repeat any of those edges, right? Okay, so that's it. So for the Euler's circuit.